Welcome. In previous video, we looked at the steady state drawdown. Now we will look at drawdown as it is changing with time. Okay. And we will see the equations for this. So the previous equation, it used to be like Siemens equation. And you learned how to use Siemens equation to estimate, for example, like you are giving transmissivity and Q, and then you can estimate drawdown, for example. Or if you are giving drawdown and Q, then you can estimate transmissivity, similar to what we do in a pumping test. Or if you are doing like transmissivity and drawdowns, then you can estimate Q. In this video, we'll look at another equation like called like C's equation, not SEAM, or C's solution for confined aquifer for estimating transient drawdown. So basically, like if I know like T, yeah, and I know Q, then I will be able to know drawdown. So if I know T, right, the transmissivity, and I know Q, how much I'm pumping, then I will be able to estimate like drawdown at any R at any distance from the pumping at any time. Yeah, that's we'll see an equation for that. Yes, there is an equation for that. We'll get drawdown or head, yeah, at any equation or time from pumping, and that's for the general case. But then we will see some special case, like for this solution. What if there were multiple wells, for example? What if there was like my boundary condition was different, like we have an impermeable boundary? What if my boundary condition has like a recharge boundary, like a stream, for example? Or what if my Q is not constant, like I have a step pumping, like so pumping goes up and down. And then we will also look at other cases like well recovery, leaky confined aquifer, and we will also look at a confined aquifer briefly. We will touch on confined aquifer. Yeah. So you'll learn how to do this in this video. Yeah. So you'll estimate drawdown for a leaky confined aquifer. You'll be able to do that. Okay. So let's get back to our equation here. So this is like two-dimensional groundwater flow in a confined aquifer. Here you have your transmissivity. Here you have your storage coefficient. We saw that this could be written in a radial coordinate. So this is Cartesian coordinate here. We can write this in a radial coordinate. Well, we've seen this in the previous video. Okay, but how to solve this guy? That's a question. Like, how do I integrate this guy? Does this guy even has an analytical solution, or I need to solve this guy numerically? Remember, we did for the groundwater flow equation. Remember to like find the solution for this guy to integrate this guy. We need to define two things. We need to define like initial condition, and we need to define like boundary condition. Okay, that's how we solve this guy. Whether we want to solve it analytically, whether we want to solve it numerically, whether we want to solve it graphically, whatever. Yeah, we need this. So initial conditions, that's simple. Yeah, for at time zero, for any r, we have like h naught. Yeah, so for all r, so that's basically very simple. Like so, at time zero, like time is equal to zero, we have like h naught here. That's our initial condition. Our boundary condition, we will assume that we have uh, this is like a boundary condition at r equal to infinity. Yeah, so at r equal to infinity, at any t, we have h naught. Yeah, so we've seen this before. So if you are pumping from here, then that's how your drawdown would look like. Yeah, that's how your drawdown will look like. So basically what we are seeing here, so that's h naught. Like so as r goes to infinity, yeah, h will be equal to like h naught. Yeah, h at r goes to infinity, h would be equal to h naught. And at the well phase, we have like Darcy law. So we assume that Darcy law is valid like at the well face. Yeah. So here is it. At the well face, we will assume that Darcy law. So basically, so this is Darcy law. Yeah, this for t for any t larger than 0, and we have seen this before. That's Darcy law. Yeah, that's like delta H over delta R, and that's 2 pi R, 2 pi TR. That's like your area time your hydraulic conductivity. Yeah, that's like here, like 2 pi R time B. That is like your area here, and then transmissivity, that's like your B time K. Yeah, so you get this equation. So we assume like that uh, for at at the well face, like Darcy law, like we have Darcy law. Okay. So given like this initial, like, so this is our governing equation here. So we have our governing equation here. Yeah. And giving this our initial and boundary condition, what Sees did, he found he didn't know how to solve this. So he knew that this equation is valid, but what he did, he didn't know, like Sees didn't know how to solve this because he was not a mathematician. Yeah, so he didn't know how to solve an equation like this. He just knows that this is true. Yeah, or like that this is the governing equation. This is what I want to solve, and he asked his mathematician friend like how to solve this, and then his mathematician friend told him you can just like rewrite, like if you have an equation that looks like this with this initial and boundary condition, you can rewrite it in this form, and this is called like an exponential integral. Yeah, an exponential integral function. So this, you can just write it in this form, and where you will basically be integrating from u to infinity. This is just like integration dummies. This is not important, and this is called like a exponential integral form, where u would be, you can define your u as something like this: r squared. So that's like r squared s, like storage coefficient 4 times t, and this is t. Big T is transmissivity, small t is time. So you just integrate from u to infinity for this one, where q here and 4t here, and that will give you your drawdown equation. And that one, that's this is the this integration has like a solution. It's not a closed form solution. It's an infinite series solution. I will show it to you in a minute. But yeah, so if I can write like these sets of equation, yeah, in this form, then that has a solution. Yeah. How to go from here to here, like how to, like the derivation, like how to write these set equation in this form, that's not important. I mean, I showed you this. I will show you this in the next slide. I got this from my lecture note when I was a student, like when I was taking a course like this as a master's student. I will show you this from my lecture note. But that is not important. Like the important thing is that you should know that this one has a solution. Like now I can express my drawdown in this form, and this one I can easily integrate this one. Okay. Here, if you are interested in the math, I got this from this is the C solution. If you are curious, like how we got from here to here uh, with this initial and boundary condition, you can check this. I can. This is my lecture note when I was a student. I can leave it. So that's when I took a course like this one. Yeah, I can leave it like more than 20 years ago, or about 20 years ago, yeah, or something like that. Yeah, not more, but about. So I can leave my lecture note, and you can read more about this if you're curious. But anyways, that's not important. Yeah, the important part is here. Yeah, is that like giving this is my governing equation. This is my initial and boundary condition. I can rewrite like this guy in this form, giving this initial and boundary condition where u is like defined like this guy, and this one here, this can be integrated. Like the integration of this guy looks something like this. And now you see here, this is called like infinite series. This is not a closed form solution anymore. So I can call like this guy is like here and this guy is here. So basically, if I integrated this guy, I would get this one. And again, this is called infinite series solution. Remember what when like the theme equation. Remember, let me show you. Like, do you remember something like this? What we did before, like Q, for example, is equals as the theme equation 2 pi r, not the theme equation, like 2 pi r t delta H over delta R. And like when you integrated this one, like if you remember, like when you integrated this one, you get something like uh, you get something like H1, for example, is equal to yeah, whatever. Like I don't remember. It was like yeah, Q over 2 pi d H R2 over R1 minus, like I think it was H2, something like this. Do you remember? And then you had something, another equation like S1, for example, is equal to H0 minus H1. See, this is called the closed form solution. Like, so if I integrated this guy, let me just write it in a different form. So I divide here by Q, and here like delta H over delta R. So when I integrate this guy, if I integrate this guy, I'll get like, see, this is called like, like the solution for this equation, the analytical solution for this equation is this one is called like a closed form solution. This is called an infinite series solution because why this is an infinite series solution, not a closed form solution? Because see here, the solution is just not something definite. It is like you get a series, yeah? You don't get a closed form. This is called like if I integrated the integration of this guy here will give me this guy here, while the integration of this guy here will give me an infinite series. So it has like, this is the first term, second term, third term, fourth term, fifth term, sixth term, and you see like here's negative and then positive and then negative, and this is to the power 2, to the power 3, to the power 4, and it goes on to infinity. And the more terms you include, the more accurate will be the solution. Versus here, you just have one solution. Yeah, here you can get different degrees of accuracy for your solution depending on how many uh, series you include in your solution. So I don't know if you did this exponential function in your calculus courses, but yeah, but that's I think that's. But anyway, so that was the solution for this, and like the mathematician friend of C's, he didn't include himself as a co-author on this paper because he told him, "Oh, this is mathematical trivialities. This is mathematically trivial." So, I mean, it's not really, I don't need to be a co-author on this publication. Actually, it was a very highly cited publication. So probably that mathematician by now is not, I think like this paper would have, I don't like, might have much higher citations than all the work that this mathematician did in his life. But because this is widely used in hydrology, like this equation in groundwater hydrology is C's solution. But anyway, so let me just summarize what we did here. So what you need to know in order you're getting lost through this mathematical detail. So this is our governing equation, yeah, with this initial condition showing how like head it changes in time. Uh, and then I can rewrite this equation. Yeah, like I can solve this equation giving this like initial and boundary condition where I have like a pumping. Pumping is occurring at the boundary. Yes, at my well here Q, and then that will take this form. Yeah, like this equation. If I giving this initial condition, it could take this form, and this equation, like to do this integration, if I integrated this guy, it looks something like this. Okay, let's look at an example. Maybe it might help you to see better. So here, this is basically the C's solution. Yeah, And the C solution to for estimating drawdown, like so we doing this here in that case we are just doing this to estimate drawdown. So that case like Q is known and T is known, and the only unknown here H node like my pre-pumping head is known, and my only thing that I want to know here is drawdown. Yeah. So I got like so that is a solution. It's called infinite series because it's not a closed form. It has many of these series, and U is given by this thing. So I can estimate Q because I know R. That's where how far I am from my pumping well. I know the storativity, I know transmissivity, and I know the time. At what time I need to look at drawdown. Yeah. So here at what distance, and here at what time I need to calculate my drawdown, my S here. Okay, so basically that's it. Yeah, like if I know like if I can calculate 1 over U, let's say 1 over U is 10, yeah? And then my WU would be like 2. Yeah, something like this. So you can either get this WU value from a graph that looks something like this, or you can just substitute it in an equation. But when you substitute in this equation, you need to determine how many terms you want to consider. So let's say I will substitute in this equation, I will consider like 1, 2, 3, 4, 5 terms. I want to include this up to 5 terms. So basically, you just substitute like this is given. You substitute your U here, you substitute your U here, you substitute your U here, you substitute your E here. Then you will get you do the calculation, you get a number, you plug it in here, and then you can do the S. Yeah, that's basically how to do. And there are also so if you don't like so you have 3 ways to find W. Yeah, so there are 3 ways to find this. If you want to find W, the first way to find like W is to use this equation. Yeah, just substitute U in your this equation, and then you get a W, and then you substitute it here. So that's number one. The second way to find W is to use like a well-functional graph figure like this. So basically, you know the U, you divide like 1 over U, and then let's say 1 over U is 1000, yeah, or 100, yeah. So you go here on this curve, oops, you go here on this curve, and then you read the value here, which would be like 3, 4, yeah. So the W before, and then you get your 4, you substitute 4 here, you know Q, you know T, you know H, you know Q, you know T, and then you can get the drawdown. Yeah. The third way to do this is you can use a table. You can use one of these tables. You can use the equation, you can use the figure, or you can use the table. Yeah. So the table basically like again like so this table show you the U value, not the 1 over U as in the figure. So let's say my U value is whatever, yeah, is let's say which one uh, like 10 to the power minus 2. Like I calculated my U value and I found it 10 to the power minus 2. So you go here to 10 to the power minus 2, and then that would be your W. Like so this is U 10 to the power minus 2. Let's make it a little bit more interesting. Yeah. So I will say like U value is 2.5 10 to the power minus 2. Yeah. So how you use this table, you go to that. This is a U 10 to the power minus 2. This is a 2.5, so it would be something in between these two here. And or let's just make it simple. Let's just make it 2, not 2.5, like 2. Yeah. So you 2, so like you go to 2 here. So for this, like your WU will be 3.55. You can also get the same number by just plugging U into this equation. So like you plug U here, 2 to the power 2. You plug it here, you plug it here, you plug it here, and you need to decide like how many terms. Maybe you stop here, yeah? And then you get a number very similar to this one. Okay. Yeah, so here I have an example. Yeah. So here I have like this example. Try to solve this example, and I will give you the solution, like my solution. Yeah. So, here I have an example. I'm telling you like u is giving as this one. So u again, how to calculate u? You know how far where you want your drawdown. You know your r. You know your time. You know your storage coefficient. You know your transmissivity. You calculate the u. So we calculated the u to be this. Like, and I'm asking you what is the wu? What is this? What is this guy here? So how to do this? Again, so like you go to 10 to the power minus 4, and then this is 4.5 to 5, so that would be something in between these two. So basically you interpolate between these two. Like, do you see my point? Let me show you. So like you say like this is at u equal to 4 10 to the power minus 4. I got like, so this is my u. This is my u. I got like wu is equal to 7.25. Yeah. At u equal to 5 10 to the power minus 4, I got my W 7.02. Now at u equal to 0.56 10 to the power minus 4, what would be this one? So you interpolate. So if you did this interpolation, I got W is equal to 0.115. So if you did this interpolation, I got something like this. Alternatively, I can just like substitute my u value here, 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 maybe stop here. And then if you did this, if you substituted u value here, you'll get a w is equal to also the same 0.115. Okay, that's how you find this. Okay, so yeah, I showed you this already. So here, this is like an example, like q is giving, t is giving, uh, storage coefficient is giving, and I'm telling you like draw down 1 kilometer from the well after 1 year. So I have a pumping well here, and I want to see like after after 1 year and 1 kilometer, how much will be like the drawdown. So how can I do this? Well, the first step is to calculate like the R. So R here is 1,000. 1 kilometer is 1,000 meters, so this is R like 1,000 meters square. S is given. T is 1 year, so you need to convert this into day, like so you need to convert this time into day. T is given, and then you calculate the U. Yeah. So if I did this, you can do it here. Like so, if I did this, I have like 365 days. This is my S is giving, my distance is giving, my T is giving the 4 years. Then I got like this number, which I showed you. And then now this is the U, but I need like my equation here is asking for the well function, like the WU. So you can do this from the equation, you can do this from the table, you can do this from the figure. Here I did it from the equation. I only took up till for 5 terms. I only took 5 terms. So basically, like I substituted this u here, I substituted this u here, I substituted this u, I substituted this u here. This here means like, like this is like 3 times 2 times 1. Yeah, so that's 6. Okay, factorial. Okay, so I substituted this here, and if you did this, you get something that looks like this. Yeah. So now I'm almost done. Yeah. Now I am almost done. I want to estimate like a drawdown. How can I do this? Uh, how can I do this? So now I have this one like 7.115. I have Q is giving, T is giving. This is known, then I can estimate this one. Yeah. So if you did this, yeah, Q is giving, T is giving. This is I got here like a different value. Like Uh, I think I got this one from interpolation, and I got this one, or actually, I just like, or you can just round it. Yeah, I just rounded this one here uh, because this I just rounded it. Yeah, like I said of 0.115, just 0.12, 1.4. Okay. Uh, Now, this equation, like which we this called like C solution, yeah. So this C solution, this is just for a single well and with certain boundary conditions that we are assuming. Like we are assuming, remember, like the boundary condition, we are assuming that at the head is known at if the head is known at the boundary. So at infinite boundary, at infinite r, the head is known, which would be like so at my boundary, I have a constant head, yeah. That's what I have at my boundary. And here I'm like here at my well, like I'm just pumping this water out, yeah. That's what I have. That's what C solution is for. But we will see now, like, what if these conditions, like, we will start to relax these assumptions one by one. So, for example, we will look, what if we don't only have one pumping well? Like, what if there are two pumping wells in the same region? Yeah. So, we will start like looking at this like multiple well system. Like, what if we have multiple well system? Yeah, not just one, but multiple well system. Yeah. How will my drawdown will look like? Yeah, we will start to see like what if q is not constant, for example, like we relax this assumption. What if my boundary, like, so remember that's my boundary condition here, I have like a constant head. What if I have a different boundary? Like what if I have an impermeable boundary? Yeah, where impermeable boundary, remember, so that's like my boundary is not like a constant head anymore. My boundary is um, now it's a type 2 and Q would be equal to 0, like flow would be equal to 0. Or what if I have like a stream that is like constantly like recharging my aquifer like after like this drawdown. So we will look at all these special cases. That's what I want you to look at because when we get to next lesson and learn about pumping test, I will show you like how when you conduct a pumping test. So pumping test basically what we do, like let me tell, we have like a whole series of lecture about pumping test, but let me just introduce it now and tell you why do we do pumping test. So pumping test, we keep pumping the water, like pumping the water, and we keep observing drawdown. So like we start here, we pump, and then we see like after some time it's here, after some time it's here, after some time it's here, after some time it's here. So we keep like observing this drawdown with time. That's a pumping test. And why do we do this? Like why do we need to do this? We need to do this because we want to estimate, like we know Q, we know S, and we want to estimate T and the storativity. Yeah, that's why we do a pumping test. But from a pumping test, we can also learn about other things. We can learn if we have an impermeable boundary, if we have a leaky aquifer, if we have all like these things, we can learn it also from pumping tests. But I will just like start like just giving you this conceptual background now, and then later when we get to the pumping test, you will see the practical application of what you're learning here. So it's very important. Yeah. But here, that's like a single well. Uh, so we've seen this before. So for a single well, like if I want to say like what's the drawdown here at this distance, at R1 distance, at after 1 year, we know this already. Yeah, we know Q, we know T, and then we can calculate this one. But now here, let's look at this. Now we see solution for multiple well systems. So I have here this guy, I have a pumping well here with Q1, I have another guy here with like Q2, and now I'm telling you, so drawdown here would be known, like you just use like C's equation. Drawdown here would be known, like you use C's equation. But what about here, like this area? So like in this area, you need to know what exactly is happening. So from this area, like let's say what's the drawdown here, which is like here. How did we get to this point? So basically this point, you just assume, like let's assume this guy's not here. If this guy's not here, then what would be the drawdown here? The drawdown here would be something like this. Yeah. Now let's assume that this guy is not here. If this guy is not here, then what would be the drawdown here? The drawdown here would be something like this. And so now what would be the total drawdown? The total drawdown would be the drawdown from this guy caused by this guy plus the drawdown caused by This guy. That's it. And that's how we got this point. This is a drawdown like here. Like see this drawdown caused by this guy. And this drawdown here caused by this guy. The combination of these two will give you this point. Similarly here. So you see here, uh, you have like the similarly here, so similarly here. That's a combination of like the drawdown by this guy plus the drawdown by this guy that will give you this drawdown here. That's basically what we have here. So total, my drawdown is S1 plus S2. That's it. Yeah, that's really it. And then you can have like like you can just put this in the general form. So that's if in like two wells, like let's say you have 10 wells, and that would be the basically the Q, the pumping rate in each well. Transmissivity is constant across your aquifer, and there's a WI here that would be how far uh, uh, your R, like your point here, like the points that you are interested here from each of these wells. Yeah, and then the T is constant and the S is constant. Yeah, okay, T is time. Yeah, okay. Now let's look at something else. Let's look at if what if we have an impermeable boundary. Uh, so this is like a constant head boundary, but here's an impermeable boundary, like a no flow uh, boundary. So in that case, how do we solve this? So to solve this, there like you do a trick. Yeah, you assume that like okay, this is my pumping well. Yeah, so this is my pumping well. And then just like let's say this is my impermeable boundary is acting here, like my impermeable boundary is effective here. Yeah. And then you mirror this pumping well. And this would be assuming that like so you are pumping from here, yeah, you are pumping from here, and then water is getting supplied from here. But you are pumping from here, water is not getting supplied from here. Yeah, you're not getting any supply from here. So you assume that whatever pumping you are pumping from here will be just like will be removed, like it will not be replenished anymore, as if you have like a mirror of this one, and as if you have like an equivalent one who's just like pumping here. And that's basically like how you account for this impermeable boundary. So let's do this again. So here from this side, this is like your regular C solution. Yeah? From the impermeable boundary side, you don't get the regular C solution, but you just get like much steeper drawdown because it's not like the water is not getting replenished. Yeah. So you got this much steeper drawdown, and that's how we estimate this. So basically, the drawdown here, it will be the pumping you are doing from here plus the mirror one, like you mirror it, and like the uh, you assume that's like the pumping that's doing from here because not getting replenished anymore, as if you are pumping, like you are accounting for this. I mean, you just like you need to think about it, yeah. Just thinking about it a little bit, and then Q is the same. Q is the same, and here this is would be the WI, uh, and this would be different because the R would be different, like how far, like this uh, R from like your impermeable boundary. Yeah, how far your observation point is from this impermeable boundary. Because remember, R1, this is how far, like R1 would be how far your observation point from the well. Yeah. But this one would be like how far your observation point from like this impermeable boundary. Yeah. Okay. That's how you get like your R1. Okay. So that's now let's look at the opposite case. Let's look if the Q, like if your boundary is actually you have a perennial like let's say like stream where you pump the water and then the water will be replenished from this stream. And remember we call this like groundwater capture, and I told you sometimes you pump the water and you're not taking water from storage, you're just taking water from here. So like you see here, your drawdown is steep because I'm dewatering this guy. I'm like taking water from storage. While you see here, drawdown here, you don't have any drawdown here. Drawdown here is very small because most of the water that I'm getting, I'm not dewatering the aquifer. I'm not taking this water from storage. I'm capturing this water from somewhere else. So in that case, I will be capturing this water from this stream. Uh, and in that case, like, remember the mirroring method. So here we also do a mirroring method, but you invert it. So you mirror and then you inverted it. So you mirror left to right and then you invert it like top to bottom, because now you don't have like drawdown, now you have recharge. So now something extra is coming from here. So that is basically like in the previous equation, when you have an impermeable boundary, that was plus, like you have this drawdown plus this drawdown. But now you imagine here that you have like an injection site, for example, like you imagine this as an injection site, which is like replenishing your aquifer. Yeah. So you have a negative drawdown here. So that's basically would look very similar to the previous one, except that you have this negative sign here. Now, here, this is what I want to show you. So if you are doing a pumping test, that's like the theoretical curve would be something like this. So this is the time, and this is the drawdown, like your S. So at the beginning, like let's say the time begin like 1 minute, yeah, you have this drawdown. And as time go, your drawdown will increase, yeah. You get more like your head, like, so you start here and then let's say like I'm looking at this point. After some time it will be here, after some time it will be here. That's my drawdown. My drawdown will keep increasing, yeah. Now here, if I have a recharge boundary, then my drawdown will like reach like a plateau, yeah, because now after some time the boundary effect started to appear, and then I started to get recharge from this boundary, and then I will might like reach a plateau like this. While if I have impermeable boundary, like no draw with barrier boundary, like impermeable boundaries, then my after sometimes after the effect of this boundary start to kick in, my my drop down would be much higher, because this water is not getting replenished, so the water table will just keep declining and declining and declining more and more, not reaching a plateau here. So for example, like let's look at this time step, like after 300, yeah. So at this time step, for example, see the drawdown here with recharge is about like 10, like let's say 10 meter. The theoretical one is about like 11 meter, while for this one it's about like 11.5 meter. And now when we do pumping tests, this theoretical drawdown is generally known, yeah. I'll talk about pumping this next series of video. This theoretical drawdown is known, but we can know if we have like a recharge boundary or impermeable boundary by just comparing the drawdowns that we are getting with the theoretical one. So if we got like less drawdowns, then we say, oh, there's an impermeable boundary in the subsurface. Or there is like, if there is a recharge boundary, like we will know that, okay, we are taking water from the nearby stream or lake or whatever, yeah, which would you expect. And if you are doing a pumping test near like a stream or lake, you need to account for this in your analysis of your pumping test result. But again, we'll talk about this next, yeah. Okay, so I think that's we can also do step pumping. Like in the previous cases, we assume that the pumping was constant. What if pumping was not constant? Well, doesn't matter, yeah. You just add like, so the drawdown would be like, so you see here, this is my pumping rate. I'm starting like I'm pumping at 5 meter cube per day, yeah. I'm pumping at 5 meter cube per day. So I keep pumping, I have drawdown, 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 yeah. And then now I step down my pumping, like my pumping went from like 5 to like 3.5, yeah. Then I step down my pumping, and then I will the drawdown now will recover. So this is like a recovery, yeah. So I will be like in a recovery phase. It will not be that big drawdown, and then I will keep pumping, and then I will have like some little bit like steep, like it's going up, not very steep. It's like upward trending or even like plateau, and then I step up my pumping. So you see my drawdown will increase, and then my drawdown will increase. I step down my pumping, and then my drawdown will increase, and then I step up. Yeah. So how to do this? That should be easy. Yeah, because you just like add them. But except here, this is your Q node. Here, this is your Q1. That's the difference. So Q1, that would be like, so Q1 here in that example, for example, like if I'm looking at from here to here, so that would be like 3.5 minus 5, and that will give me negative 1.5. And that's how exactly I got, like, see, I got this drop. I'm getting this negative drawdown. Yeah. Here I got like it will be positive. Here it will be negative. Here it will be positive, and so on and so forth. So that's basically, and the other thing here is like T. That's the T here. That would be like your time. That's your cumulative time. So you need to account for like your cumulative time, and you need to account for Q. Okay, that's for the case of step pumping. You can also do recovery, and so that's like the drawdown. Like I start pumping, and then drawdown will increase, 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 increase. Then I stopped pumping here, and once I stopped pumping, what will happen? My water level will start to go up again. My water table will start to go up again, again, again. So my water table will decrease. And that's important also when you do a pumping test. So you remember I told you in the pumping test, you you start pumping at a constant rate and you record the drawdown. And then you stop pumping. But when you stop pumping, why don't you continue also recording the recovery? Like how your water table is going up again after you stop pumping. And then you will have two set of data, like drawdown, like and residual drawdown. So the residual drawdown, that's like the opposite of drawdown, like it's recovery. Yeah. So the residual. So here, like my water table is going up. Residual drawdown, that's when it's going like my water table is going down, and residual drawdown, that's like the opposite or inverse drawdown. That would be when your water table go up again. Then you will have two set of data, and then you can analyze them. And we will talk about pumping tests and analysis of pumping test data like in the next video. But here, like the only, so now here that's your drawdown, and that's like your recovery or residual drawdown. For the residual drawdown, T is the time since the shutdown. So that's here T is like the time since the beginning, but here T is the time since the drawdown. Yeah, the shutdown. Okay. Let's look at other cases. So we looked at different cases where we have like recharge at our boundary or impermeable boundary or something like this. But for the unconfined aquifer, we also uh, we also remember this is a confining layer, and sometimes I told you there might be some vertical recharge from here. It could be small, but there could be, this is called like you have like this leaky aquifer where you have like this little vertical recharge from here. So you're getting your main recharge from here, like through your boundary, but you also have some vertical recharge from here. Do we have an equation for this? Yes, we have an equation for this. So basically, like your well function will now be like, will have like this extra term here, like R over B. What is R and what is B? Like R, we know R. Like R is a distance from like where we are observing the drawdown. But what's B? B here, this is basically transmissivity, like the transmissivity of the aquifer, and the saturate is the thickness of the confining layer and the hydraulic conductivity of the confining layer. So basically, if this guy, like if this is equal to zero, let's say almost equal to zero, like this is like there's no recharge from here, there's no flow, it's completely confining layer, no leakage. Yeah, if this is equal to zero, then what will happen? Yeah, then this guy, yeah, B will like this guy will be approach zero, and you'll get like the C solution, like where you don't have any recharge, like you don't have recharge from here. Yeah. So that is the case when when that's the case when when k like when k here is equal, like k prime here is equal to 0, and then you'll get the C solution. Otherwise you will get like this well function here. Yeah. Okay, but what is this well function? How does it look like? Well, let me show you. It looks something like this. Yeah. So this is like your R over B. Yeah. So this is like you here you have like high leaking. And here this would be like when R over B like approaches like 0. That's like, so that would be the C solution. Like you see here, remember the C's curve? Like you have like W, U, and 1 over U. So that would be, sorry, that would be like your C's curve. And that would be like different curves for different R over B value. Yeah. And we can look at and so here this is an example. Like let's look at this example, like example of a leaky aquifer. So Q is constant. So Q is constant. The time is 30 days, like after 1 month. So we are pumping this rate for 1 month. The transmissivity of the aquifer is known. The storage coefficient is known. The thickness of the confining layer is known. The hydraulic conductivity of the confining layer, see, is very small. It's known. And then I'm telling you, I want to calculate like the drawdown at different distances from this pumping well. So at the 50 feet, 100 feet, 250 feet, 500 feet, so on and so forth. I want you to calculate. And as we expect, like the maximum drawdown be like close to the pumping well. At very far away from the pumping well, the drawdown will be 0. Yeah. But how to do this? Yeah. So that's simple. So we calculate like the B. So B, that's like T transmissivity, the thickness of the confining layer, the hydraulic conductivity of the confining layer. So you put this number here, then you get like a B value. Yeah. And then you get R over B, like the distance where I am observing drawdown divided by B. So you divide like this guy by this guy. Yeah. And then you calculate your U. That's like we did this before. Like U, that's like R. That's like R is the distance here. The S is giving, the T is giving, and the time is giving, which is 30 days or whatever. Yeah. So and make sure that your units are consistent when you calculate. Then you calculate the U. Yeah. And then like how to find this guy? Well, to find this guy, you just need to go to a table that looks like this. So let's look at an example. Like let's try to find like this guy here. Maybe this one is easy. Yeah. That's like, so I calculated like this is giving, the U is giving, like I drag in my number here. So the U is giving. So now I have this one. Yeah. Let's see here. So the U is giving as this number here, 1 over U, like you divide this by 1 over U. R is giving like 0.89. So R here, like we calculated R, yeah, is giving. And then basically you just try to find it like, so the W, so 1 over U here, and you find like this R over B curve. So these are the R over B curves. So we have like about like 0.9. So this is 1 here. This is like, see, this is 1 here. This is 0.8 here. So maybe 0.9 would be like this one here, something in between. Yeah. And then you get like about 1. Okay, but of course this is very tedious, yeah, especially like this is on a log scale. So what we generally do, we solve this problem with the software, which we will learn like when we do the pumping test, is called Aquatisolve. Yeah, but I'm just showing you this as an example. But anyway, so you got like W is equal to 1. So like if you look here at this example, so you got like WU, yeah, almost 1. Yeah, and then you just like now you have an equation. Now this is easy. So here, like this guy here is like 1 or point like 0.99, for example. Q is given, the T is given, then that S would be like 2.44 feet. So here, like the drawdown near like 50 feet away from this pumping is about like 16 feet. About like 1,000 feet away from this pumping is about 2.44 feet. And the further you go away from where you are pumping, which you can see here, so that's the maximum drawdown here, 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 here. The further you go away, then the drawdown here is almost zero. Yeah. Okay. So I think that's yeah. So this is this. We looked at this already. Now there is we've looked so far. This is for so we looked at different cases. Yeah, we looked at the confined confined aquifer with leaky, like a leaky confined aquifer. What about the unconfined aquifer? So for the unconfined aquifer, I just want you to be aware of this because we'll do this later in detail. We'll talk about this in detail when we get to the pumping test. Uh, then I just want to show you it is just the same business. Yeah. So you have a different well function. So like you have like for the original C solution, you have this well function. For the leaky aquifer, you have this well function like R over B. Here you have this well function with which has now like three terms. So like C is getting a little bit more interesting. It has like UA, UB, not just like so this is WU, this is WU of this is my first parameter and this is the second parameter. Here now I have UA, UB, and like this gamma. So UA, that is for early drawdown. This is for later drawdown. And then this UB is telling you something about how this gamma function it captures. So that's like early drawdown. Remember early drawdown, that's like when you take water, like compressed water, and that would be like you have this storage coefficient. Later drawdown, now you have a specific yield term here. So this storage coefficient is specific yield here. And here, like this gamma function has to do with horizontal hydraulic conductivity versus vertical hydraulic conductivity. So if they are like different, like to account for this anisotropy, like if it is anisotropic, so you also account for this isotropic, and this is your initial saturated thickness, and this is R is the same. Yeah. So 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 I just want to like to summarize. I just what I want to tell you is that like for each one, like the equation looks the same, like this well function would be different. So this well function for the confined, this is the well function for the unconfined, this is the well function for the leaky confined aquifer. Yeah. Do we have other solution? Yes. So these are just some analytical solutions. We here see this is analytical solution. All of them are infinite series, and I showed you why they're infinite series because you just get these series and you select up to what accuracy do you want. Uh, 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 other well analytical solution to calculate drawdown, like if you want, also other solution could include like partially penetrating well, 2 or 3D layer system, like you don't only have one homogeneous hydraulic conductivity, but three different hydraulic conductivity at each layer, for example. Large diameter well, like if your well has like a large diameter, and saturated and unsaturated conditions. So there are analytical solution for pumping for all these cases. I'm not going to show them to you here, but I will show you like a software like later called AquatiSolve that will have all these solutions already built in. You just put your data and it will do the analysis for you, the pumping test analysis for you. But we will do so. That's what we will be doing next, like a pumping test. And so basically, what we learned in these series of video, you will apply them to do aquifer test, and these aquifer tests, that would be like your first step to characterize your aquifer and to do modeling. So that like starting from like next videos, we will start to get more into like less of this conceptual understanding and we'll get more into more practical application until like the until you at the end of the semester you will be developing groundwater model by yourself. Yeah, you get it, all this data and develop groundwater model. Okay, so that's basically how this course is projecting from like a conceptual understanding to more authentic or like real life learning. It's called authentic learning or real life application. Okay, real life cases or real life scenarios. Okay, so that's it, and like see you in the next video to learn about pumping tests.